That's recording. Today we're going to finish main memory, hopefully. We may have a couple of other lectures, maybe guest lectures talking about deeper topics into main memory. And we'll at some point talk about emerging technologies later on in the semester. Maybe soon. I haven't decided yet. But we'll continue where we left off on memory scheduling. You guys had 2 guest lectures so far, right? Was it interesting? Like what kind of things were happening in DRAM? Yeah, it's a hot time for DRAM today because previously changing DRAM was considered like a taboo because DRAM manufacturers were scaling the circuit really well and they didn't have any issues in increasing the density, reducing the size of the DRAM cell. But now scaling that cell beyond 30 nanometers, lower than 30 nanometer feature size has become very, very difficult. So now even DRAM manufacturers who have been making money out of Moore's law being applied to the circuitry are having trouble improving the performance and energy efficiency of the cell itself as well as the density. So they're now looking into other ways of thinking about DRAM. Can we do more with DRAM? And some of the things that you've heard, Vivek, for example, gave background on how DRAM actually operates internally, the subarray structure of DRAM. And he took advantage of it to actually do bulk copy and initialization of data, which is actually a pretty cool idea, I think. It's not done today, but going forward, doing such operations within DRAM, such that you take advantage of the internal bandwidth in DRAM at very low cost makes a lot of sense, right? Because why move the data all the way to the processor if you're not going to use it for any computation? Just do the data movement and maybe some of the computation within DRAM such that you don't actually exercise the interconnects and consume a lot of power across the entire memory hierarchy. So you heard all about that. So thinking new ways of using DRAM, new interfaces, new functionalities within DRAM is a very hot thing to do today, especially because business as usual is not working and we're running into energy limitations. And data movement is one of the most expensive things that you have in a computing system today. It's really cheap actually to, in terms of energy, to do an add compared to move 8 bits of data across from the memory interface into the processor. So you'd rather not move the data, do the computation locally, and somehow partition your computation across your accelerators such that they can do their computations locally and communicate as little as possible. When we talk about heterogeneous systems, we'll get back to that. But thinking from that point of view is very interesting today. The other thing you heard was TLDRAM, tiered latency DRAM, that Donghyuk talked about. And there, you're trying to get the best of both worlds, right? Best of both latency and density area. You like to minimize both. But it's impossible to minimize both at the same time, so he designed a heterogeneous structure. He segmented the bit lines, created a portion within DRAM that's closer to the sense amplifiers that can be accessed much faster by turning off the isolation transistor. And if you wanted capacity, you can turn on the isolation transistor and access the entire bit line. This is a heterogeneous structure. And whenever you're trying to optimize best of both worlds, or get the best of both worlds, or optimize for multiple metrics, you might want to think about heterogeneity. That's a very good principle to employ. And I'll show you an example, actually, very soon in the lecture that employs heterogeneity in memory scheduling, building upon the last lecture. In the last lecture, Justin discussed memory interference in multi-core systems. Was that interesting? You guys? Yeah, that's another important problem that has appeared with the prevalence of multi-core systems. And we had talked about that before, very early on in the first lecture, right? What happens to MATLAB versus GCC, right? You remember that. And he's proposed some solutions to the problem that we have developed over time, and some of the ideas are being employed in existing systems today. And we'll continue that today. We'll look at better ways of designing memory schedulers such that they can handle interference and they can cater to needs of different applications in better ways. And then we're also going to talk about different ways of handling memory interference. And then I'm going to wrap up with some of the other issues in DRAM, other ways of looking into memory controllers. And we'll talk about refresh. Hopefully we'll get to that. Okay? Any questions from previous lectures? Should we have a review session sometime to go over what we've covered? Okay. I see a lot of heads nodding, so we'll do that sometime. Okay, now let's jump into today's lecture. Well, before that, I guess, there's an upcoming seminar. If you're interested in DRAM and these topics, there's a seminar tomorrow at 4 p.m. in this room by Professor Balasubramanian from University of Utah, exactly on the same topics that we've been discussing, memory architectures for emerging technologies and workloads. And he'll be talking about some of the things they've been exploring in DRAM in terms of heterogeneity, how to take advantage of the heterogeneity in DRAM in terms of latency. They've been looking at near data processing also, similar to the row clone ideas, but in a different way, and memory security, which we have not talked about. So this should be interesting, hopefully, to many of you. And I definitely encourage you to attend. And there's a Cloud workshop all day on April 4th. I haven't decided whether we should have the review session that day or we should cancel class. What do you guys think? So if I take a vote on canceling class, I'm scared now. Do you prefer to attend this or have a review session? I know Rachada wants to attend this. A review session?
I'll go with Rachada.
You'll go with Rachada. Wow. Okay. Who else wants to go with Rachada? Let's see. Some of you don't care.
Does this mean we don't get a review session?
That's right. Yes. If Rachada goes, there's no review session.
Actually,
Okay.
there's a closer session right before the class started that you guys come on the 10th day that our project is working on how we're doing.
Oh, okay. Yeah. So maybe this is a better way, and we'll have a review session some other time. Let's see. So let me think about this. But even if we have class, there are other talks that are going on, and I would encourage you to attend. For example, some of these are, like I'll be talking about rethinking memory system design. Rajiv is talking about memory security, future of NVM memories, non-volatile memory technologies. We haven't covered that, but we'll cover that later on. Online transaction processing on non-volatile memories. Professor Paulo is talking about that. The impact of flash memory on the future of cloud computing. So these are actually very interesting talks. And you can see some of the other ones are more cloud-oriented, scheduling heterogeneous resource in cloud data centers. So I definitely encourage you to attend this one. You can still register. And there's also a career fair, I guess part of which is during class time, which you can go to. Okay, so let's jump into where we left off. Remember, Justin talked about parallelism over batch scheduling, which you all know by heart now, right? What that was. There were two main ideas. You batched requests and serviced that the oldest batch before any other batch, such that you guarantee forward progress. Okay. And the second idea was preserving parallelism, right? Parallelism awareness. Basically, the idea was to rank the threads and service the threads in that rank order within a batch, such that you would preserve the parallelism and enable shorter jobs to process faster, such that you could maximize performance. I'm not going to go over that again. You can look at the slides and read the lecture, but this was the first scheduler to address bank parallelism destruction across multiple threads. Because if you actually do not preserve bank level parallelism, you can delay all of the threads. It was a simple mechanism compared to stall time fair memory scheduler that we also discussed. And batching provided starvation freedom as well as fairness. And ranking enables parallelism awareness, which I just talked about. The downsides of this approach was, I think Justin talked about this, but if you want to have multiple memory controllers, which is a reality in today's systems, this needs coordination for the best performance. Because how do you actually determine a good ranking across different controllers? How do you form a batch when requests are going to different controllers, right? One thread may have only one request in one controller, but may have 100 requests in the other controller. How do you determine that rank? So you need some coordination such that you have a globally optimal or globally good scheduling mechanism. And the other downside is actually this, which is this does not always prioritize the latency-sensitive applications, and that's why it doesn't improve performance significantly. An application is latency-sensitive if you have requests that need to be serviced quickly, such that the application can go back to computation in its core. And usually applications, so of course latency sensitivity is a matter of usage pattern also. You may care, for example, about the time it takes for the computer to respond. That's an inherent latency sensitivity characteristic. But assuming all applications are equal for some reason, an application for which a memory request enables the core to stay busy for a long time is more latency sensitive than another application that's where a memory request doesn't enable the core to stay busy for a long time. Basically, you service a memory request, and then the application can go ahead and do a lot of work. That's more of a latency sensitive application. whereas you service a memory request from another application, and the application quickly generates another memory request. Well, it's going to wait for the one of the memory requests anyway, right? So this doesn't prioritize the latency-sensitive applications because it does batching, right? Batching says even if you have a latency-sensitive, even if you have an application that has one request, if it's not in the batch, it's not going to be serviced, unless it goes to a bank that's not busy at that point in time, right? Okay. So thread cluster memory scheduling is the last memory scheduler that we will talk about. Is advances the state of the art by solving these two problems. And we'll see how it does that. Did you cover this slide last time? Probably not, right? Not yet. So what we're trying to balance is really throughput versus fairness. And these go against each other in many times. So here I show you different memory schedulers and their performance in terms of system throughput. And we can go into metrics some other time, but you can read the papers to figure out the metric. But assume that this is a good metric for performance. You get better system throughput as you go from left to right, and you get better fairness as you go from top to bottom. And fairness is maximum slowdown in this case. What is the slowdown of the application that has been slowed down the most compared to when it's run alone in the system? And these are simulation results across 96 workloads on a 24-core system with 4 memory controllers. Ideally, you would like to be here, right? Highest performance, highest fairness. Let's see where these schedulers that we've discussed fare. Atlas we have not discussed, actually. It's a scheduler that basically ranks the applications based on their attained service. How many requests were serviced in the previous interval from an application? If an application has fewer requests that are serviced, prioritize that application in the next interval. It still uses the ranking idea that we've discussed. It's biased towards system throughput because it prioritizes these applications that do not we demand a lot from memory. And we just discussed that those applications are the ones you would like to prioritize because they can go back to their cores and keep computation units busy. So it has a system throughput bias. You cannot see it over here. But PAR-BS, which we just discussed, has a fairness bias. It doesn't have as high throughput, but it's much more fair. STFM, stall time fair memory scheduler, which we also discussed, I guess it's not ideal, right? It doesn't exceed these schedules in any way. First ready, first come, first serve, which is usually implemented in today's systems, which we've discussed, basically is up there. It's not good for performance or fairness. And this is first come, first serve. At least on these workloads, it stays over here. So it's not that good. If you look at this, there's no previous memory scheduling algorithm that provides the best performance and system throughput at the same time. Basically, that should be somewhere here. So we would like to achieve that. So how can we achieve that? It's always good to strive for that ideal, right? That's how we can advance the state of the art. Let's think about these two different approaches. You can have a throughput-biased approach or fairness-biased approach. And different schedulers are biased in some way. If you want to have a throughput-biased approach, if you want to improve system throughput, you would really like to prioritize the less memory-intensive threads. If you think about threads this way, and if you look at their intensity, memory intensity, thread A is not very memory-intensive. Prioritizing thread A is good. Ranking it higher is good because it can service, its request will be serviced early and it can keep its computation unit busy. Less memory intensive means more computation intensive. This is good for throughput. This is bad for this thread C because now thread C starves, right, if you actually provide a ranking like this, because there will be many, many threads that are serviced before thread C. This leads to unfairness. If you want to have a pure fairness-based approach, one idea of fairness is to do round-robin scheduling, right? Basically, provide turns to each thread such that it can access memory for a while. It can be the highest ranked thread for a while. Now, this is good for thread C because it becomes the highest ranked thread once in a while and it doesn't starve, whereas it starves over here because its ranking never changes. But this is bad for thread A because thread A becomes the top thread only once in a while. Right? Whereas you really would like to get it serviced quickly such that it can keep its cores busy. So this kind of points to the fact that a single policy for all threads is insufficient. A single policy cannot optimize for throughput and fairness at the same time, or at least it's very difficult. We do not know of a way to do that. So how do you actually optimize for both? Well, I just gave you the principle, right? Heterogeneity. So we would like to design a heterogeneous policy. So the realization is that if you would like to improve throughput, we would like to prioritize these memory non-intensive threads. And for fairness, we realize that the unfairness is really caused by memory-intensive threads being prioritized over each other. So it doesn't cause unfairness prioritizing these little threads, if you will, doesn't cause significant unfairness to these threads because these have few requests to begin with. Whereas if you prioritize one of these threads consistently over another thread, it causes a lot of unfairness because this has a lot of requests, a lot of memory bandwidth demand. So the idea is to be fair, we'd like to shuffle the ranking of these threads periodically. And that's the idea. This gives you, and there's asymmetric shuffling because threads have different vulnerability to interference too, but we're not going to talk about that right now. But that's the idea, basically. The idea is to group the threads into two clusters based on their latency sensitivity or memory intensity, if you will. These are the threads in the system. Memory non-intensive threads, memory intensive threads are grouped into two clusters, non-intensive cluster and intensive cluster. And non-intensive cluster is prioritized over the intensive cluster because these are threads that can keep their cores busy much more. And we employ different policies within each cluster. Within this cluster, the memory scheduler prioritizes the less intensive threads over others, so there's a ranking that looks like this. And within the intensive cluster, threads priorities are shuffled. Ranking is shuffled such that each thread gets its chance to be the top thread that is prioritized. Make sense? So that's the basically heterogeneous policy. So how do you actually do this? Let's go into a little bit more detail. We'd like to cluster the threads, as I told you. How do you cluster the threads? Well, you can first sort the threads based on their memory intensity. Misses per kilo instruction, the last level cache. And you can see it over here. And then you can compute a total memory bandwidth usage across all of those threads, how many bytes per second, let's say. And then dedicate some amount of that, divide that memory bandwidth usage across these clusters. And you can have a threshold across that total memory bandwidth usage and say threads that consume approximately 10% of the total memory bandwidth usage are designated as being in the non-intensive cluster. Basically, the idea is to have few threads that are not very intensive in this cluster and prioritize them such that they can make fast progress and be fair across all of these other threads such that all of the threads can make progress. Okay. This is actually kind of similar to how operating system schedulers work also. They usually prioritize latency sensitive applications that can make progress and can keep their cores busy. And they're usually fair across all of the other applications that are usually not able to keep their cores very busy. Okay? Or they're actually very intensive in terms of keeping their cores busy because that's the operating system scheduler, right? Some of the threads may hog the cores because they're very long running. Okay. So, any questions so far? So principles are clear, right? Okay. So how do you how do you actually implement this? How do you actually figure out how do you do this? Well, this is happening at a very fine granularity. Remember, this is not at the operating system level. This is at the nanosecond, millisecond level. Basically, the idea is to do quantum-based operation. You learn about the characteristics of the threads in a previous quantum on the order of 1 million cycles. Monitor the thread behavior, memory intensity, bank-level parallelism, and robot locality. And these are needed for different kinds of shuffling mechanisms. So you don't need to understand this at this point. But you can look at the paper if you want more detail. And at the end of the quantum, the memory controller in hardware performs clustering of the threads, as I discussed. And again, this is needed for better shuffling. And it divides the quantum into shuffle intervals that are much smaller than the 1 million cycles. And the idea of shuffle interval is during each interval you have a different permutation of the intensive cluster, the ranking of the intensive cluster. So very fine grained, at very fine grained, every 1,000 cycles you have a different ranking, such that these big threads that demand a lot from memory don't destroy each other's performance. Okay? And that's the scheduling algorithm. Basically, it's, again, every scheduling algorithm is this prioritization order as we discussed earlier. And the prioritization order looks like this. Highest ranked threads, requests from higher ranked threads are prioritized. And ranking is determined this way. Non-intensive cluster is higher than intensive cluster. Within the non-intensive cluster, lower intensity threads have a higher rank. And within the intensive cluster, we do rank shuffling. And assuming everything over here is equal, row buffer hit requests are prioritized over others. And assuming everything up here is equal, all the requests are prioritized over others. Make sense? We still want to exploit row buffer locality, obviously. Okay, so where does this kind of scheduler. I'm not going into a lot of implementation details, but if you're interested in it, you can read the paper. The key principles should be clear to you, though. Where does this put us? Let's take a look at all of these other schedulers. This is the figure I showed you earlier. I guess a little bit zoomed in figure. If you actually implement TCM, this is where you what you get. Basically, you kind of break the trade-off, right? Of course, it's not on every benchmark you do well, but on average, this is what you get. So a heterogeneous scheduling policy provides the best fairness and system throughput compared to all of these different homogeneous scheduling policies. Why is this heterogeneous? Because it applies a different policy depending on the intensity of the thread, right? Depending on different clusters, you have different policies. Whereas in PARBS, you have the same policy across all of the threads. Across different batches, you do different things, but that doesn't consider threads. Okay. You can actually vary the configuration parameter of these memory controllers. For example, in PARBS, how big should your batch be? Right? That's a configuration parameter. If it's too big, then you may have a problem because these non-intensive threads may have a request, and you have a huge batch that you need to finish before a single request from that non-intensive thread gets served. If it's too small, then you don't exploit bank-level parallelism memory overflow locality really well. So going forward, a lot of the parameters of memory controllers will be varied. And these controllers actually have parameters that can be varied. Stall time fair memory scheduler, the unfairness parameter, unfairness threshold, if you remember, that can be varied. Even first ready, first come, first serve. Robo for hits, which prioritizes only robo for hits over robo for misses. The parameter can be varied. Basically, how many requests can bypass the oldest requests is a parameter that can be varied in first ready, first come, first serve. And if you vary that, this is the kind of trade-off that you get between system throughput and fairness. And if you vary STFM, this is the kind of trade-off you get. It's kind of unpredictable, right? It's a really odd curve. PARBS, if you vary the batching cap, or marking cap, that's what you get. In Atlas, you didn't know about it, but if you vary the interval size, that's what you get. With thread cluster memory scheduling, if you vary the cluster threshold, this is what you get. So it's kind of a Pareto curve, right? Pareto optimal curve. All of these points may be good depending on whether you're optimizing for fairness or throughput. So ideally, you would like to design a controller that behaves nicely like this, such that the operating system can say, oh, I want more fairness, or I want more throughput at the expense of fairness. It can pick one of these points. So whenever you're designing controllers, keep that in mind. Okay, so it provides a robust fairness throughput trade-off. One side note going forward, these controllers are becoming more and more sophisticated, right, as we go along. They can incorporate priorities, as we discussed. They can incorporate like thresholds in terms of fairness. And in the future, hopefully, they'll incorporate more and more. And but when you want to do processing close to data, having this logic within the controllers can be useful to do some processing as well. So this gives you a good argument for having memory controllers that will do processing into the future too. Because you already need to do some processing to provide quality of service to different applications. Okay, let's take a look at the upsides, pros and cons of thread cluster memory scheduling. Well, the upside is it provides both high fairness and high performance, on average at least. And also caters to the needs for different types of threads. Some threads are latency sensitive, some threads are bandwidth sensitive. And in general, assuming all threads are equal priority, the ones that have few memory requests are more latency sensitive. The ones that have lots of memory requests are bandwidth sensitive because they demand a lot of bandwidth. The latency of one request is not as important because they have memory level parallelism, right, as we've discussed, because you can overlap those requests. And it's relatively simple, especially compared to stall time fair memory scheduling, although it's not as simple as it could be. So striving for even simpler is better. There are some downsides. How do you actually scale this to large buffer sizes is something you can think about. I'm not going to go into detail. And how robust is this clustering and shuffling algorithm? This is actually a problem with this kind of approaches. Whenever you want to cluster threads into two clusters, well, where do you make the cutoff, right? What if you make the cutoff here, and what happens to the thread that just doesn't make it barely? So you can actually get slowdowns on those threads that are just at the cutoff. Okay. Any questions? Okay. So this is one other thing I will mention is one of the things that's interesting that we have not discussed is today memory is shared by heterogeneous processors. It's not homogeneous processors, but you have GPUs and CPUs sharing memory. And those different processors have different needs as well. GPU, for example, is more bandwidth sensitive, whereas CPUs could be bandwidth sensitive or latency sensitive. So this kind of approaches that treat threads differently are even more amenable and desirable for those systems that have heterogeneous cores. And Archada has actually worked on some problems related to that. He can tell you more about that, perhaps in the review session. Okay. Let's take a look at some other ways of handling memory interference, because this is going to be a growing problem as we push forward, as we keep adding more cores. As we keep adding more threads also, in a fine-grained multi-thread machine or simultaneously multi-thread machine, you have threads that are interfering with each other, even at the core level. So how do we handle, what are some of the general ways to handle memory interference? One of the things that we've looked at is prioritization or request scheduling, right? Basically scheduling requests such that you minimize the interference or minimize the slowdowns due to interference. We'll take a look at a couple of other approaches. One is data mapping, intelligent data mapping, or partitioning of data across banks, channels, or ranks. And we'll talk about channel partitioning in a little bit more detail. The other is core or source throttling. Basically, instead of doing request scheduling, why don't we throttle the sources, cores, such that they don't send a lot of requests if they're being harmful. And the other is application or thread scheduling onto the cores. Maybe it's a good idea to put applications that do not harm each other onto the cores and schedule them together, right? If you have that flexibility. And you may have that flexibility in a data center, for example. If you have a data center scheduler that receives some requests, it knows some things about the requests, and it's trying to make the decision, should I put all of these requests into this machine or this machine? If it can estimate that these requests, these set of requests interact nicely with each other in the memory system, it can say, oh, I'll put all of these requests into this machine, instead of putting requests randomly to different machines and without knowing the interactions that will happen between the threads. So this could be amenable in places like data centers, but you need to do some characterization of the threads as they come in. Okay, let's take a look at the second approach, data mapping to banks, channels, and ranks. So today's memory systems are multiple channels. We've covered that earlier. And this provides a new degree of freedom for handling interference. And the idea is to map data across multiple channels. In many systems today, data is mapped like this. Basically, data of different applications are spread across all of the channels. And this causes interference between different applications requests. So if we are aware, if we make the operating system aware of these different channels, maybe the operating system can do something like this, right? It can partition channels between different applications. In this case, if you look at this, the red application doesn't interfere with the blue application, and blue application doesn't interfere with the red application. If you can do this, that's great. Now this is a toy example because you don't have systems with 2 cores and 2 channels, right? That would be nice. You usually have systems with many cores than number of channels. Then the key question is how do you partition the channels across different applications? So I'll give you some principles for that. I'm not going to go into detail. But the goal of memory channel partitioning is to eliminate harmful interference between applications. The basic idea is to map the data of badly interfering applications to different channels. And the key is here, badly interfering. Obviously, you're not going to be able to dedicate a channel to each application. In fact, that may be a bad idea because you may want to have an application's request spread across different channels such that you have better channel level parallelism for that application, right? You don't want to get channel level conflicts. I don't know why this is moving by itself. I usually don't like that. Let's see. Any ideas? Is it slideshow? There you go. Wow. Oh. That's not what I wanted. Okay. So what is badly interfering? Basically, I actually kind of told you that, right? If an application has high intensity and another application has low intensity, you don't want to put them into the same channel, assuming your memory scheduler is prioritizing, is not aware of applications, right? Is not aware of threads. And even if it's aware, actually, this is not a good idea. If an application has low robuffer locality and another application has high robuffer locality, you don't want to put them together on the same channel because assuming your memory scheduler is first ready, first come, first served, it will prioritize the application that has high robuffer locality. So we'd like to group the applications such that these applications are separated in terms of memory intensity, as well as applications are separated in terms of robust locality. Those are the key principles. And I guess I'll give you one example of this, for example, here. This is the first insight. Separate applications by memory intensity. Assume that this red application is very intensive. It has lots of requests. And blue application is not very intensive. It has only one request over here. If you actually separate them to different channels, both applications win. Right? You can save cycles on both applications. Because here, this blue application gets delayed, and also the red application gets delayed because they contend for the same band. Okay? That's the first principle. Map data of low and high memory intensity applications to different channels. Of course, somebody needs to determine this intensity. The second is high robust locality applications interfere with low robust locality applications in the memory channels. And separating them is a good idea. And you can take a look at these two applications. Well, what is this? This is a request buffer state, and these are the rows that the requests are going to. The red application goes to row 0, the blue application goes to different rows. And this is what you get with conventional page mapping when they actually interfere with the channels. If you actually separate these applications to different channels, this is what you get. Again, both applications' performance, well, I guess this one doesn't improve, but this application improves. Okay? Does that make sense? That's the idea. So how do you actually go about doing this? I'll give you the basic principles again. Today's operating systems, actually, you don't have a whole lot of control across the channels because remember our discussion earlier in the memory mapping, virtual to physical mapping, and DRAM address mapping. This channel bit needs to be known to the operating system to be able to do this page mapping. Right? And today, that bit is not known. Well, if you have only one channel, you have one bit. But if you have multiple channels, you have more than one bit. So the operating system may have control, but may not be able to do that today. Okay, so how do you do that? Basically, first we need a way of profiling applications, figuring out their memory intensity as well as row buffer locality. And then we need to classify applications into groups and partition channels between application groups and assign a preferred channel to each application. And whenever that application needs to allocate a page, the operating system allocates application pages from that preferred channel. That way you can partition the channels. Why is it preferred? Why is it not hard-coded? Well, because if you actually say, I can only allocate pages from this channel, then you're really hard partitioning your memory across applications, right? And an application may demand more memory than one channel may have. That's why hard partitioning is usually not a good idea. That's why this is preferred. If an application cannot allocate a page from that preferred channel, it'll allocate a page from some other channel. This will cause some interference, but hopefully it'll save some page faults. You don't want to get a page fault to reduce the interference a little. Okay, so you can divide the work between the hardware and software actually at any level here. But it makes sense to do it this way. Profiling is done in hardware because that's such a fine-grained thing. What's the memory intensity of an application? What's the row buffer locality? In fact, operating system doesn't have any visibility without any hardware counters. And the rest can be done by the system software. So this is a hardware-software cooperative approach. Basically, within an interval, the hardware can profile the applications. At the end of the interval, it can communicate this profile to the system software. And the system software can classify applications into groups, partition channels between groups, and assign preferred channel to applications. Now each application now has a preferred channel. And the next interval, when the application needs to allocate a page, the system software says, okay, I'm going to enforce the channel preferences that were assigned at the beginning. This is one way of doing the operation. Does that make sense? It's similar to TCM at a different granularity, of course. Okay, so that's the idea. This way you can keep your memory scheduler simple, as it is today, but handle memory interference at the operating system level. Well, hardware, software, cooperative manner. This may not be ideal, though, because applications with very low memory intensity rarely access memory, as we've discussed, right? And dedicating channels to them, even though there may be a lot of such applications, you may be wasting precious memory bandwidth, right? You have some bandwidth in your channel, peak bandwidth, and you're putting all of these low memory intensity applications there, which are not using memory that much. So maybe it's not a good idea to handle these applications in this way. And at the same time, these applications are the most potential to keep their cores busy. Why? Because they have few requests, and after their requests are serviced, they can keep their cores busy. So we'd really like to prioritize them. So And on top of this, they interfere minimally with other applications because they're low memory intensity, right? Prioritizing them doesn't hurt other applications. So a better idea, combining memory scheduling and memory partitioning, is to actually do this. Always prioritize very low memory intensity applications in the memory scheduler. So memory scheduler figures out those applications that are very low memory intensity and has a bit distinguishing them from all of the other applications and prioritizes them. And use memory channel partitioning to mitigate interference between other applications. So that's another way of handling things heterogeneously. Right? Because these applications have these characteristics, low memory intensity applications have these characteristics, treat them differently. Prioritize them in the memory scheduler. That's good for system performance, fairness, and also that helps bandwidth partitioning because you don't waste bandwidth in the memory. And treat the other applications differently. Use memory channel partitioning, as I discussed earlier, to mitigate the interference between other applications. Make sense? So it's another heterogeneous policy. And this is called integrated memory partitioning and scheduling. And it turns out this actually provides better performance than previous memory scheduling approaches because it's a more balanced mechanism. It reduces interference. If you actually just, if you have a lot of interference and try to solve that interference by prioritization, you can only go some way, right? Because there's some fundamental interference you cannot eliminate. If two things conflict in a bank, well, you cannot eliminate that conflict with just scheduling. But if you do partitioning, you eliminate bank conflicts. Okay? Any questions? No. So of course, one question I will tell you is, well, I may ask you, what should be the granularity of interleaving data across different channels for this to work? So for the operating system to be able to partition channels across different applications, where should the channel bits come from? In the virtual or physical address. Can the operating system do this if some of the channel bits actually come from the page offset? No, it cannot, right? You're shaking your head. Because the operating system has control at the page granularity or larger granularity. If you're actually interleaving one cache block, if the hardware is picking the channel bit such that this cache block goes to this channel, this cache block goes to the next cache block goes to this channel, the next cache block goes to the other channel. It's basically interleaving cache blocks across channels. The operating system cannot do this at all. Okay? So basically, cache block interleaving across channels does not work with memory partitioning, or memory partitioning does not work on a system that does cache block interleaving across channels. And there's a trade-off there. Cache block interleaving across channels may be a good idea because now if you have multiple cache blocks, consecutive cache blocks, and if you're accessing them in parallel, concurrently, you can bring them in parallel across different channels. So that's good for bandwidth. But you cannot do interference control in this manner. So there's a trade-off. Okay. Let's take a look at another approach. And these four are four fundamental approaches for interference control. If you come up with other approaches, let me know. You can apply this to other kinds of interference that happens. For example, let's say in the future you're designing SSD controllers, flash controllers. Well, you may need to look at some of these mechanisms to actually reduce interference. Operating systems, again, you may need to look at some of these mechanisms. It depends on your shared resource, but most shared resources, you should be able to employ these techniques to reduce interference. So the third technique is core source throttling. I've given you the basic idea very briefly. The idea is to, instead of managing the interference that happens between threads or applications at the shared resources, that's what the memory scheduling does, manage it at the cores. Basically, somehow dynamically estimate unfairness in the memory system, feedback this information to a controller, and the controller will throttle the core's memory access rates accordingly to optimize a goal. And this goal can be flexible. Basically, whom to throttle and by how much depends on performance target. If you're optimizing for throughput, fairness, per thread performance, the target could be different. Or what you throttle, whom you throttle, and how much, by how much it could be different. So, for example, if the unfairness that you measure by this dynamic estimation mechanism is greater than some system software specified target, then you can throttle down the core that's causing the unfairness by limiting its request rate to the memory system. How do you do that? Basically, you say, this core, you've been causing a lot of unfairness, so you cannot inject to memory in the next, I don't know, 1 millisecond. Maybe that's too long, but 10,000 cycles. There needs to be those thresholds that need to be optimized, of course. This way, that core will not be causing unfairness in the next 10,000 cycles, right? Because it's not injecting into memory. And throttle up the core that was unfairly treated. Allow it to request more. Allow it to access memory more frequently, if it needs to. That's the idea. That's the idea of source throttling. Basically, instead of, if you think of shared resources as a cloud like this, it could be memory, it could be something else, and cores, which could be different, as agents injecting into this cloud. One way is to prioritize these requests, accept all of the requests that are coming in, and prioritize them internally to reduce interference. That's kind of like memory scheduling, right? Then it's the memory controller over here. The other way is to collect information over here and then tell the cores, well, you're not allowed to inject for a while. Or you can only inject so many requests in the next so many cycles, right? That's the idea. That's the idea of managing interference at the periphery rather than the shared resources. Okay. In fact, the internet kind of does this, right? Congestion control in the internet today happens this way, and you can think of internet as routers. And if there's TCP, for example, transmission control protocol, operates this way. If there's too much congestion that's detected, if your round trip delays are increasing, then the sources are throttled such that they don't inject a lot more packets into the network. You could apply that principle to a small scale system like this too. Make sense? I'd actually recommend, if you haven't taken a networks course, I'd recommend taking networks courses, because interference is a big issue in networks also. How do you provide quality of service within the internet to different streams? Those routers need to be aware of the different flows coming from different parts, and they employ prioritization. They employ core throttling or source throttling to accomplish quality of service. Okay, this is the paper if you're interested. But let's take a look at how this operates. So this is also interval based. Within an interval, and this is one way of doing this, but within an interval you can estimate the slowdown of different applications that are sharing the memory resources. Let's call this runtime unfairness evaluation. During that interval, the hardware can find the application with the highest slowdown, and it also finds the application causing the most interference for that application with the highest slowdown. Let's call the application with the highest slowdown as app slowest, application with the highest interference for that application as app interfering. At the end of the interval, it sends an unfairness estimate, and the application that has been slowed down the most, and an application that has been interfering the most with that application, to an engine, dynamic request throttling engine. And the dynamic request throttling engine makes a decision based on this information. Okay. If the unfairness estimate that's provided is greater than some target, there could be other conditions over here. Then it throttles down the application interfering that has been causing the most interference by saying you cannot inject more than this much in the next interval. By limiting injection rates and parallelism, you could actually limit the number of MSHRs, miss buffers, you dedicate to, not dedicate, but this application can use. And throttles up application slopes. Basically, it increases its injection rate, the maximum injection rate, and increases the number of MSHRs it can use. Okay? Okay, I think we've already discussed this. Estimate the slowdown due to interference and throttle down threads that slow down others. I'm not going to go into the results, but this actually works well compared to memory scheduling mechanisms. The advantages, this is actually easy to implement. There's no need to change the memory scheduling algorithm. This is actually similar to channel partitioning. Again, channel partitioning, you don't need to change the memory scheduling algorithm if you're doing well. But if you want to get even better performance, you may want to change it a little bit, as we discussed. It can be a general way of handling shared resource contention, as I discussed over here, right, with the internet. The downside is it requires these interference or slowdown estimations, basically which applications are being slowed down and which applications are causing that slowdown. And even though the throttling itself is easy to implement, this estimation mechanism may be difficult to get correct. Remember in the stall time fair memory scheduler, we tried to do this. We tried to estimate the slowdowns. It's actually complicated to do that. How do you actually estimate the slowdown of a thread perfectly compared to when it's running alone? Well, you need to account for all of those interference sources. If you really, really want to do this perfectly, maybe you're really emulating a system that is running only that application. And emulating that system in hardware is basically the same as building that system in hardware, which is what you want to avoid in the first place. That's a lot of hardware, basically, if you want to do this perfectly. If you take shortcuts to do this, then your unfairness or slowdown estimations may not be accurate. Okay, so that's a disadvantage. You need some accurate slowdown estimates. And also, I haven't gone into detail, but I've given you an example. How much do you throttle each core? How do you actually limit these injection rates? Well, you need a threshold for that, right? And these thresholds can become difficult to optimize. Whenever you have these thresholds that say, oh, you're not going to inject in the next few cycles, then the question is, how many requests should I inject? Right? Can that core inject? So it becomes, for example, if you disallow a core from injecting for a very long time, you may lose throughput because the interference may have gone, but this core is not injecting. So even though you have resources available without interference, this core is disallowed to inject. Right? So these thresholds usually lead to throughput loss. And whenever you have threshold-based mechanisms, you have this kind of problem. Okay? And the internet has the same problem, actually. When do you actually tell a stream to stop injecting, and when do you tell a stream to continue injecting? Right? How do you actually do the rate control? Okay. The last idea, I'm not going to go into detail on this one a lot, is application thread scheduling, but I gave you the basic idea. Pick the threads that do not badly interfere with each other to be scheduled together on cores sharing the memory system. Right? If you have this flexibility, this is great. Let's say you have 1,000 threads, and you would like to schedule them on a 4-core machine. Which threads do you pick? Well, hopefully you pick the threads that will not interfere a lot with each other. Maybe you pick all low memory intensity threads, right? Or maybe you pick high memory intensity threads that have good robot for locality, all of them, such that one of them doesn't deny service to the other one. Right? So there are heuristics to be developed here, such that the operating system thread scheduler is contention aware, or data center's request scheduler is contention aware whenever it tries to schedule requests. If you do this, you can minimize the interference that happens in the memory system such that threads can progress well because they do not interact with each other badly. Does this make sense? Okay. We're not going to go into detail on this one, but there's something good to think about. One other thing I would like to cover before we take a break is handling interference in parallel applications. So far, we've been talking about different applications, right? Different threads. They don't have anything to do with each other. But life is not that simple. The problem is actually much more complicated than what we've discussed. If you have a multi-thread application where multiple threads are cooperating to solve a problem, these threads are interdependent on each other, right? For example, you may have a thread holding a lock, and many threads may be waiting for that lock, right? In that case, that thread that's holding the lock may be the most important thread. Maybe you would like to prioritize that memory request coming from that thread in lieu of requests coming from other threads. Right? That's the idea. Locks are one of the synchronization primitives, and the other synchronization primitive that's important is barriers. Basically, let's say you've started a bunch of threads, and some of the threads reach a barrier early, and the idea is to wait for those other threads before you can make progress, right? If this thread is waiting for all of those other threads before it can make progress, now all of these other threads are kind of limiter threads, right? They have a lot of requests that are pending. This thread is making good progress, but it's already waiting. So you would like to you would like to prioritize the thread that's making the slowest progress, that's furthest away from the barrier, right? So that's the idea, because these threads need to synchronize when they come to a barrier. In a sense, if you would like to somehow design a memory scheduler, at some point we'll have some of these working. Maybe I'll put it over here. Let's say you have a program with 4 threads, and you would like to schedule the threads or design a memory scheduler such that it can balance these different threads' progress, right? If they're all balanced like this somehow, you can save a lot of cycles, right? Assuming this is time over here, and these are the progress of different threads. Let's say thread 0 through thread 3. For some reason, this thread is thread 3 is making slow progress because these threads have hogged the memory bandwidth, right? If that's the case, you may want to prioritize this thread and deprioritize some of these threads and kind of balance the progress of the different threads such that they all reach the barrier at the same time. Make sense? Have you guys done barrier-based programming before? Yeah? Some of you. Okay. Okay, maybe we'll talk about this in more detail when we get to heterogeneous systems. But basically, in a barrier-based program, all of the threads need to reach a barrier before moving on to the next step of the program. Assume what the favorite example I give over here is you have a problem. Let's say you're counting the number of A's, B's, C's, the number of each character in a book. Right? How many times do you have A's occurring, B's occurring, C's occurring, D's occurring, dot, dot, dot? You can partition this problem such that you have multiple threads. Let's say you decided to have 4 threads and you have 100 pages in a book. The first thread can count the occurrence of different letters in the first 25 pages. The next thread can count the occurrence of each letter, the distribution of each letter, or histogram of each letter in the next 25 pages. The next thread in the next 25 pages, the next thread in the next 25 pages. Right? Now you partition the problem. And each thread at the end generates a histogram. And then you may have a single thread that takes those histograms and adds them up, such that you have the final histogram. Final count for each letter across the entire 100 pages. Well, before you start this thread, you need a barrier. You need to be sure that all of the threads have generated their histograms. This is one way of programming this, to solve this problem. There are actually more smarter ways to do that, but I'll give you the one that actually requires a barrier that looks like this. So that requires a barrier. All of the threads need to finish their histograms before this thread can add them up. That's one example. And there are many problems that can be partitioned this way. And in this case, the thread's progress may depend on how much memory interference you have, because all of them are accessing these different pages, and they may be located in similar banks, and they may have different localities over here, because in one page, for example, you have lots of A's. In one page, you may have all pictures, right? You may not add anything to the histogram. The distributions of these letters may be different across different pages. That leads to locality differences. As a result, these threads may interfere differently. And if you have a memory scheduler that can recognize the threads that are lagging, it can prioritize those threads over others such that all threads reach the barrier around the same time without one thread delaying another thread significantly. So that's the idea. In a parallel application, you may want to have a different approach. Basically, some threads can be on the critical path of execution due to synchronization. Some threads may not be. In fact, some of them may be on the critical path because they just happen to have bigger load, right? Maybe the first 25 pages you've assigned to this thread have all pictures, right? Then that thread will be done very quickly. Which means that this thread has some slack, right? You can delay it a little bit without affecting performance significantly. So why not prioritize another thread that has a lot more work to finish to reach that barrier? And the key question is, how do we schedule the request of these interdependent threads to maximize multi-threaded application performance? I'm not going to go into this question in detail, but actually we're going to look at similar mechanisms to schedule threads to different cores, large cores versus small cores. But the basic idea is estimate the limiter threads that are likely to be on the critical path. For example, a thread that's holding a lock and all of the threads are waiting for it, it's likely on the critical path. Estimate those threads and prioritize their requests. Then the key question, this way you can ensure that the critical path of the program is accelerated, assuming you can do this estimation accurately. And then the question is, what do you do with the other threads, non-limiter threads? Well, you want to make sure that they do not become limiter threads. And the idea over here is similar to thread cluster memory scheduling, if you will. Shuffle the priorities of the non-limiter threads to reduce memory interference among them, such that they all make some progress. Okay? So how do you estimate the limiter threads? we'll get to this a little bit when we talk about heterogeneous systems. But threads that are executing the most contended critical sections are usually limiter threads. A thread that's falling behind the most in a parallel for loop, that's farthest away from the barrier, is usually a limiter thread. Okay? If you want more information, I can definitely talk to you about which papers to read. But one big question, so this is multi-thread applications. The systems, the real systems that we have are not only multi-thread, but multi-programmed. You have some applications that are single-threaded, some applications that are multi-threaded that look like this, and you mix them together on your laptop and maybe in a data center as well. Then the key question is, how do you actually design these interference control mechanisms such that you can handle all of those different applications well? I'm not going to answer that. But I'll leave you with this. The best is actually to combine all of these mechanisms. There's no single way of handling interference that clearly outperforms the others. The best is to have a good mechanism that combines all of them. Then the key question is, how would you actually do that? Well, that really depends on your system design, and I guess depending on whether or not you solve this problem in the future. Maybe you can think about maybe you'll develop a mechanism that actually combines them in a good way. But for example, we've discussed how to combine prioritization and data mapping together, right? You partition the memory channels across relatively high intensity applications, but prioritize low memory intensity applications in the memory scheduler. Right? That's a combination. You could actually do the throttling. Whenever memory system load is very high, you could put in application source throttling mechanisms can kick in. And thread scheduling is usually a good idea. If you can do this, this is usually a good idea. That way you can avoid interference as early as possible. Okay. Any questions on interference? It's actually a fascinating topic. We could go on and on interference, because it's so much prevalent in many systems you design. Whenever you have a shared resource that's being accessed by multiple, and you can pick your favorite shared resource and you can pick your favorite multiples. It could be humans, right? Also, a lot of the issues come about because they're shared resource and there's interference for those shared resources, right? How do you actually enable fairness to those shared resources? So it's the same problem that happens in computers also. So it's a fascinating problem to solve. It's not going to go away. Okay. Shall we take a break for 5 minutes and come back and finish the DRAM controllers? I guess what is that? Maybe 40 according, 38 according to that.
Yeah,
it's kind of late.
Yeah.
But
All right.
So for the last
They're
one.
usually pretty ugly. That's
Okay.
someone knows it.
Let's keep going. Guess you guys are excited about the lab, huh? It's good. It's fun to test your own lab. Okay, let's keep going on memory controllers. I'd like to cover a little bit more, give you some more ideas on system design, stretch your minds a little bit. Because there will be a lot of changes to memory system and memory controllers going forward. It's good to think about different ideas. And then we'll talk about DRAM refresh. One of the things that we have not talked about is DRAM power management. That's one of the duties of the memory controller. Basically, DRAM chips have power modes, and this is the only slide I have on this. You can read more if you would like to. But the idea is to, when you're not accessing a chip, power it down. If you know how long you're not going to access a chip, power it down as long as that duration, right? Wouldn't it be nice to do that? You can power down disks, for example. Why not power down DRAM banks also? Well, today, the granularity is not at the bank level. So the granularity is really at the rank level. You can do rank level power management in DRAM. But going forward, perhaps bank level granularity may be interesting. And today, their power states are not a lot. So active is obviously the highest power. You can access any bank. All banks could be idle. Then the power consumption is lower because you're not drawing a lot of current. There's a power down state when the row buffers are actually pre-charged, meaning there are no open row buffers. That consumes less power. And if, for example, the DRAM controller figures out that there's not going to be a request to the row buffers at this time, it can close the row buffers, right? It can pre-charge the banks. And self-refresh is the lowest power state in which DRAM chip basically doesn't accept any request but keeps refreshing the rows to keep the data intact. And you can transition between these different states, but they incur latency during which the chip cannot be accessed. For example, during self-refresh, you cannot access DRAM banks. And most of the time, probably this is in self-refresh. It's not operating from the disk or SSD, but it's really keeping the data in memory such that it can respond to calls and can respond to your demands. But it's refreshing DRAM. But of course, the latency transition from self-refresh to power down or self-refresh to active is relatively long. Because self-refresh means shut off all the circuitry in DRAM, but enable just the refresh circuit. Remember the refresh circuitry that we saw in that complicated DRAM diagram? Basically enable all of that. Everything else is clock gated, such that the clock doesn't even go there. So you'll need to wake up the DRAM chip such that it does something else other than self-refresh. But this is actually going to be interesting going forward. So we've been looking at doing voltage and frequency scaling within DRAM, such that you can change the voltage and frequency of the memory bus. That way you can save a lot of power also, because high frequency buses consume a lot of energy. Remember the power equation that we wrote down at some point in time? Dynamic power is proportional to capacitance, voltage squared frequency. And if you have large buses that have high frequency, this needs to be high. And for this to be high, your voltage supply needs to be high. So you have a cubic relationship between frequency and power. And if you can actually reduce the voltage and frequency of the DRAM buses, especially when you don't need them, you can save significant energy. Right? Especially when you're not accessing them a whole lot. Right? So your bandwidth demand is not high. So that's another way of doing power management. But this is again under the control of the memory controller. The DRAM controllers have this task as well going forward. And increasingly this will be important because power is a key concern in memory systems and systems in general. So let me go into a little bit more as to why DRAM controllers are difficult to design. First of all, you need to obey DRAM timing constraints for correctness, and I'll show you some examples. There are many timing constraints in DRAM. One of them is write to read. I briefly mentioned that last time. It's the minimum number of cycles to wait before issuing a read command after a write command is issued, so that the bus can be turned around. Right? The circuitry to drive the bus needs to be turned around, and this takes time. TRC is the minimum number of cycles between the issuing of 2 consecutive activate commands to the same bank. Right? You need to prepare the bank for the next access. And it takes some time to stabilize the bit lines. As a result, you have this TRC. Right? And there are many, many other timing constraints in DRAM to accomplish this. And the controller needs to handle all of these. It needs to keep track of many resources to prevent conflicts. It could be channels, banks, ranks, data bus, address bus, row buffers. If subarrays are exposed, subarrays. What transactions are going between the different subarrays if you're doing row clone, for example. It needs to handle DRAM refresh. It needs to manage power consumption. And if you have voltage and frequency scaling, it needs to dynamically scale voltage and frequency. And all along, it needs to optimize for performance. Basically, what we've talked about was performance before, in the presence of all of these constraints. And as we've seen, reordering is not simple. Like we've talked about 3 major algorithms to actually do reordering. Right? Even then, it's those are not the best because they do not take into account the full complexity of the system, multi-thread applications, for example. And fairness and quality of service needs complicate the scheduling problem also. So for all of these reasons, it's difficult to design DRAM controllers. And these are some of the examples of the timing constraints. These are only a few of them. For example, you have activate to read write, write column address stroke. 4 activate windows. This is a power-related constraint, for example. You can do 4 activates. You can issue 4 activates commands within 24 cycles. You cannot issue a 5th activate command because that puts too much burden on the power circuitry in DRAM. And that basically, the DRAM manufacturers do not guarantee operation if you actually issue a 5th activate command within this timing constraint. Because you're drawing a lot of power, right? By doing each activate, it's a lot of power. Write recovery time. After you do a write, when can you issue a read command? Well, because once you do a write, you're actually driving the circuits, and you need to recover from that. And that takes a long time. So all of these commands, somehow the controllers you design, or the poor DRAM controller designer designs, need to obey these. And if you would like to learn about some of these constraints, these 2 papers, actually a tiered latency DRAM paper has this figure that shows what are these different timing constraints. It doesn't cover, of course, the 60+ timing constraints that are present in DRAM controllers today, but it covers the major ones. So given this, whenever you have a complex system, it may be good to take a step back and say, oh, can we do something better? And we've done that, and we've come up with this idea. So I'll describe you the idea, just to stretch your mind. Whenever you have complex systems, it may be good to take a step back and try to optimize things in a different way. Basically, DRAM controllers are difficult to design. So it's difficult for human designers to design a policy that can adapt itself very well to different workloads and different system conditions. So FRF-CFS is one human design policy, for example. It's very simple because humans are not good at designing extremely complex things that can take into account many things. Well, they are good at designing things that can design things, perhaps. So we're going to take advantage of that. Basically, design a memory controller that adapts its scheduling policy decisions to workload behavior and system conditions using machine learning. Instead of fixing the policy, why don't we say these are the inputs and these are the outputs we want, and somehow we're going to employ a machine learning algorithm that can optimize for this. It may not always work. I wish everything worked this way, but it doesn't always work. So observation is that reinforcement learning maps nicely to memory control. What is reinforcement learning? Basically, you're in a state, you take some action, and you learn whether you get reward from that action or not. Your reward is your reinforcement, right? And it is if you get a reward, you learn to repeat that action if you are in that same state again. If you keep getting that reward, now you're reinforced to take the same action over and over when you're in that state. Right? Just like Pavlov's dogs. Are you familiar with Pavlov's dogs? Basically, whenever the bell rings, they know that the food is coming. Right? So they become obedient. It's the same thing, basically reinforcement learning, except it's applied to machines. So a memory controller is a reinforcement learning agent that dynamically and continuously learns and employs the best scheduling policy. And it turns out this problem maps well to the memory controller. Reinforcement learning in general, you have an agent that hopefully learns. It takes an action, and environment responds in some way. It gives a reward, or it doesn't give a reward, and the action is taken in that state. And the agent learns that if it keeps making the same action in that state, it'll be rewarded. This is Pavlov's dog, right? You're hungry. Well, I guess the bell doesn't work too well over here, but that's okay. in that case, you don't wait for the bell, but you actually be obedient and maybe ask for food and be obedient, and you get the reward. And you keep doing that, you get rewarded. That's the idea. And the memory scheduler actually maps nicely to this because it turns out for reinforcement learning to work well, it needs to be a Markov decision process. And I'm not going to go into that in detail. You can read the paper related to this. But basically, you can think of the scheduler as an agent that, based on some state attributes, takes an action, and the system responds with some reward value. In this case, reward value can be data bus utilization, if you want to maximize data bus utilization, for example. And then the scheduler learns to associate the state's action pairs with the rewards, and tries to, at any given state, it has a choice of actions and picks the action that maximizes the reward. And the reward function can be complicated. Basically, you would really like to maximize a long-term reward. You don't want to maximize a short-term reward, because short-term reward may be, do you utilize the data bus at this point, right? After this command. But not all commands utilize the data bus, right? Sometimes you may want to close a row, pre-charge the bank, and in the long run, this will enable maximization of the data bus, because it will reduce a bank conflict. It doesn't immediately optimize the data bus utilization, but in the long run, it optimizes the data bus utilization because you close the row, which enabled another access to a different row to proceed right away after it came. So it's important to maximize a longer-term reward, which means that reward at time 0 plus some factor times reward at time 1 plus some factor times reward at time 2, ... So you need to keep track of this. So there's some overhead associated with this. That's the idea, basically. Dynamically adapt the memory scheduling policy via interaction with the system at runtime. The DRAM scheduler associates system states and actions with long-term reward values. It schedules a command with the highest estimated long-term value in each state. And it continuously updates state action values based on feedback from the system. Right. At this state action pair, what is the long-term reward? Okay. Of course, if you need to pick the state attributes well, you need to, well, schedule commands are available at that point in time. And reward function you need to determine when you design such a controller. And that's the paper that describes the controller. I'm not going to go into detail, but I'll give you what kind of things can be states, actions, and rewards. So reward function, if you want to maximize data bus utilization, we can have a value +1 for scheduling read and write commands. Basically, you would really like to, in the long term, maximize the scheduling of read and write commands, right? Data bus utilization. And you get 0 reward at all other times. Immediately you may get 0 reward, but that may lead to a lot of ones later on. State attributes, what are these? Well, actually, you can do feature selection on these. That's another machine learning method to figure out what are the most interesting state attributes to input to the controller. It could be number of reads, number of writes, load misses in the transaction queue. So these could be input. Number of pending writes, and reorder buffer heads waiting for the reference row. This tells you how critical the requests are. And request relative order in the reorder buffer, because this tells you how critical the request may be, right? Or how critical the request may become. And these are actually the attributes that we selected among a set of 400 or so attributes in the system. You can imagine any kind of attribute in this system, right? That could be exposed to the memory scheduler. But you can do this feature selection offline to figure out what are the most interesting features. And actions are, these are some of the actions that the controller optimizes for. Activate, read, write, reads, load miss, read store miss, precharge, and preemptive precharge. Precharge pending means you precharge a bank for which there's a pending request, and precharge preemptive means you precharge a bank even though there's no pending request to that bank. And the memory scheduler can also issue a no-op. Sometimes you may want to skip and not do anything. Right? Okay, so if you actually design a controller like this that operates based on these principles, it actually performs really well. These are some parallel applications, multi-threaded applications, and this is geometric mean results among them. I believe these are 8-core results. I'm not sure though. But basically this is in-order scheduling, first come, first serve. That's the execution time. No, this is performance. First ready, first come, first serve, omit first scheduling improves performance significantly on these workloads. And if you do reinforcement-based scheduling, reinforcement learning-based, you get approximately 19% performance, which is pretty respectable actually. This 70% is the ideal you can get. Basically, what if you eliminate all of the timing constraints other than data bus as a constraint, data bus conflicts? Yes?
Do these memory-based learning controllers, are they non-volatile across multiple program runs, or do they sort of reinitialize for each
That's it. That's a good question. They reinitialize in our experiments. But you could imagine learning and saving the state as part of your context. That way you need some more operating system support, or you need to have some non-volatile memory on chip to do that. But in this case, they reinitialize, they relearn. That's a good point. If you actually have non-volatile state associated with memory scheduling, then you can actually save some time for learning. The upside of this is there's so much data going into the memory scheduler that relearning doesn't take a whole lot of time, because there are lots of requests that are being generated. And these are results with multiple channels. You can take a look at that. So let's take a look at what are the advantages and disadvantages. The advantage is this adapts the scheduling policy dynamically to the changing workload behavior to maximize a long-term target. So it doesn't fix the scheduling policy. There's no human designer that fixes scheduling policy. Scheduling policy, in fact, we do not know what the scheduling policy is. It's all determined based on this table that associates state action pairs to values, to long-term reward values. And if you're more interested in this, you can take a look at the paper. And I definitely recommend that you take a machine learning course at some point too, because systems are becoming increasingly complex. And some of these approaches could be useful for you whenever you're designing complex systems. The other advantage is it reduces the designer's burden in finding a good scheduling policy. Now the designer doesn't need to find a policy that works for most of the workloads and most of the time, depending on the changing workload demands. But they just need to specify, I guess I need to change my battery, what system variables might be useful to consider in memory scheduling, and what performance target to optimize for, but not how to optimize it. The difficult part is really the how part. Which request do you schedule? Or like what action do you take? So hopefully the designer's burden is much less in the presence of all of these constraints. The disadvantage is this is usually a big disadvantage whenever you employ machine learning techniques. It's a black box, right? You don't know what the underlying controller is really doing. The designers, as a result, a system designer is much less likely to implement what she cannot easily reason about. Because you cannot reason about what's going on with the scheduling policy, right? It's optimizing for some reward value. It's trying to maximize that and associating some state action pairs with the reward values, but at any point in time, you do not know what the scheduling policy is. Well, you do know what the action that's been taken is, but you cannot just say the scheduling policy is this. And this is usually a general criticism with machine learning techniques as they are employed to systems. But going forward, in many systems, interactions are so complex that using some of these methods could be very useful. For example, thread scheduling onto cores in a data center is another problem that could be very difficult because there are many things to optimize for. The other disadvantage is how do you actually specify reward functions that can achieve different objectives. Data bus utilization is a simple objective, right? Whenever you utilize data bus, great. That's what you would like to do. You want to transfer something. But what about fairness? What about quality of service? How do you actually incorporate these different reward functions into something like this? And this turns out to be not so easy to do because you need to somehow formalize this and you need to add a reward based on a target. Okay? Any questions? I just wanted to give you this idea such that hopefully this stretches your minds. Going forward, as systems becomes more and more complex, I think approaches like this will be more amenable. One of the other disadvantages is hardware cost, actually. How do you actually implement this? But the paper has a relatively simple implementation to achieve this. Okay. I guess we have time to jump into DRAM refresh in a little bit more detail. So let's go into it. Well, I think I've shown you this before, but DRAM capacitor charge leaks over time. And the memory controller needs to refresh each row periodically to restore the charge. And that's what's known as DRAM refresh. And what is DRAM refresh? Basically, you need to read each row every n milliseconds to refresh that row. Right? Just activating a row refreshes the row. That's it. Because what it does is it activates that row and connects it to the sense amplifier, and the charge out of the charge out of the cells are amplified by the sense amplifier, and the sense amplifier later drives the cells and restores the charge. That's refresh. But then you need to also pre-charge the row or pre-charge the bank such that you can prepare it for the next access. So refreshes usually activate and pre-charge each row every n milliseconds. And typical n today is 64 milliseconds. There are many downsides to this, unfortunately. You would rather have non-volatile DRAM, but we don't have it, unfortunately. Energy consumption, each refresh actually consumes energy. Activate pre-charge every 64 milliseconds. And if you have huge capacity DRAM, 1 terabyte DRAM, that's a lot of refresh operations. And 64 milliseconds is actually at the regular temperature. If you have high temperature operation, 85 degrees Celsius, this goes down to 32 milliseconds. Every 32 milliseconds you do this. Why? Because the retention time actually scales with temperature. The retention time reduces exponentially with the temperature reduction for DRAM cells. This leads to performance degradation. DRAM rank or bank is unavailable while it's being refreshed. This leads to quality of service or predictability. In fact, you can get long pause times during refresh, especially if you're not doing refresh correctly, which we will talk about. And refresh rate actually limits DRAM capacity scaling. As you increase the capacity of DRAM, the number of rows, you need to do more refreshes. Right? As you reduce the size of the DRAM cell, it becomes more leaky. The capacitor becomes more leaky, and refresh rate needs to increase going forward in the future. Okay, we already talked about this. But DRAM bank is unavailable while being refreshed. Actually, DRAM rank could be unavailable while being refreshed in existing systems because there may not be per bank refresh in some of the DRAM chips. The current DDR chips do all bank refresh. Basically, you cannot do refresh per bank. The entire rank becomes unavailable. The low power DDR chips enable you to do per bank refresh, which means that when you're doing refresh in one bank, you can access another bank. That's great. It's more finer granularity refresh. But there's more overhead into per bank refresh. You can get long pause times if you refresh all rows in bursts. Every 64 milliseconds, the DRAM will be unavailable until refresh ends. So normally, memory controllers do not do burst refresh. They used to do this in the old times. And they used to refresh all rows immediately after one another. Today, most controllers that I know of do a distributed refresh. Each row is refreshed at a different time at regular intervals. Basically, refresh is staggered across rows within the 64 milliseconds. And this is a picture from one of Micron's technical notes that showed that. If you do burst refresh, you have a refresh cycle during which you probably cannot access memory, and then you can access memory. And after 64 milliseconds, you have another refresh cycle. So you can get these long pause times during this refresh cycle. Whereas distributed refresh, we basically distribute out these refreshes across time. So this way you can eliminate long pause times. But refresh is still a problem, and I'll give you some numbers related to that. Then the key question is, how else can we reduce the effect of refresh on performance and quality of service? I guess one thing is, does distributed refresh reduce refresh impact on energy? No, right? It doesn't really reduce the refreshes. Ideally, you would like to somehow get rid of some of these refreshes. And that's what I'll talk about next. If you can somehow get rid of these refreshes, that's great. Somehow make DRAM non-volatile, that's even better, right? So briefly, just to give you the picture, today what happens is a DRAM controller periodically issues refresh commands. Today the DRAM controller doesn't know which rows are actually being refreshed. It just says refreshed. And the DRAM itself, the DRAM chip itself, has the internal circuitry that you've seen in that schematic. And it internally refreshes a batch of rows, a number of rows, via this auto refresh command when it receives that auto refresh command. So today the DRAM controller doesn't have control over which rows are being refreshed. But we can change that. We can change that interface. Maybe it's good to rethink that interface based on what I'll show you. So this is one graph that shows the overhead of refresh on performance. This is device capacity on the x-axis. How big is your DRAM chip? And this is the percentage of time the device is unavailable because it needs to do a refresh. Today, with 4 gigabit device, it's about 8%. 8% of the time, device is unavailable. This doesn't tell anything about performance. If you're not accessing that device those 8% of the time, your performance impact is 0, right? But if you happen to have a loaded system and you're accessing that, then your performance impact can be even greater than 8%. Because it all depends on what critical requests get delayed during the time the device is unavailable. In the future, if you make the projections, if you read this paper, it'll tell you more. And if you read later papers, that'll tell you more. If you build a 64 gigabit chip, 46% of the time it'll be unavailable or refreshed if you do business as usual. But hopefully, we're smarter than doing business as usual. We'll not design a chip that's unavailable almost half of its lifetime, right? And this is refresh in terms of energy, or overhead in terms of energy. Again, device capacity and percentage of DRAM energy spent refreshing. Today, it's approximately 15%, assuming some utilization. In the future, it's going to be about 50%. So how do we solve this problem? I'll give you one idea, and I hope to encourage you to think about this problem, because it's actually a difficult problem to solve in DRAM. Today, every row is refreshed at the same rate. And I think earlier, I told you that that's not the case in DRAM, right? If you look at the distribution of retention times across different rows in DRAM, it looks like this, basically. Most rows can be refreshed much less often without losing data. This is actually data from Samsung, one of Samsung's chips that was published in Electron Device Letters in 2009. If you change the refresh interval from 64 milliseconds here to 100 seconds over here, y-axis shows the cumulative cell failure probability. Basically, how many cells have failed as you keep increasing the refresh interval. Below 64 milliseconds, well, you cannot do that because DRAM manufacturers say you set the standard, right? Now, if you go a little bit above, if you make the refresh interval 256 milliseconds, if you keep issuing commands 256 milliseconds, you get only about 1,000 cells fail in a 32 gigabyte DRAM. So it's not a whole lot. And actually, most DRAM cells still retain data even at 100 seconds or 10 seconds, if you look at this graph. So the takeaway is most rows can be refreshed much less often without losing data. Why does this happen? Well, we've discussed this very early on in one of the first lectures, right? Because there's a lot of variation across the transistors and capacitors in different cells. Because they're not perfect, they're not exactly the same. They all leak at different rates. Their access transistors are leaky at different rates. As a result, you have lots of variation. Not any two cells are the same. And that variation causes these different retention times. Not all cells can retain data at the same for the same time. The problem is there's no support in DRAM for different refresh rates per row. So if you see this, you can say, oh, why don't I figure out these 1,000 rows? By the way, these are randomly distributed because the variation is relatively random. It's not controllable. It's not a systematic variation. If I figure out these 1,000 rows, why don't I refresh them at a different rate? Well, in today's DRAM systems, there's no support for different refresh rates per row. That's what we would like to achieve. Basically, the observation is that only very few rows need to be refreshed at the worst case rate. If you look at this, there are only about 30 rows that need to be refreshed more frequently than 128 milliseconds in a 32 gigabyte DRAM, and only about 1,000 rows that need to be refreshed more frequently than every 256 milliseconds. If we figure this out, can we exploit this to reduce refresh operations at low cost? And one idea you may have, and yes, you're saying, while doing your lab, this is also interesting, right? Okay, good. So the idea, yes, that's right. We talked about this before. The idea is to identify the retention time of different rows and refresh each row at the frequency it needs to be refreshed. But if you do this, then you need to associate a retention time for every single row, right? And that can have a lot of overhead. So a more cost-conscious idea is to bin the rows according to their minimum retention times and refresh the rows in each bin at the refresh rate specified for the bin. And you can take advantage of the curve that I showed you earlier. You can have a bin for rows that need to be refreshed every 64 milliseconds, another bin for rows that need to be refreshed every 128 milliseconds, and everything else gets refreshed every 256 milliseconds, right? That way you cut off your refresh rate, you reduce your refresh rate by almost 4x. Because most of the rows, an overwhelmingly large majority of the rows, do not need to be refreshed more frequently than every 256 milliseconds. That's the idea. So only very few rows need to be refreshed very frequently. You can have only a few bins. As a result, you can have low hardware overhead to achieve large reductions in refresh operations. And before we talked about, that's the idea in this paper. Before we also talked about potentially exposing this to the operating system, right? Saying that these rows actually are no good. You don't allocate to them. If you can actually do that, that's another solution to the problem. Yes?
So I can't remember whether we talked about this at the beginning or not, but where would you choose which rows to refresh when? Because the memory chip itself knows its profile, but the memory controller is on the processor of the operating system attached to the memory controller. So it seems like, and usually right now the memory chip itself controls its own refreshing.
That's right.
So where would you put this in a way that, because it seems to me like if you kept them in the memory chip, you wouldn't have that much optimization.
You could actually do this in the memory chip also. I'll show you an example. Let's defer that question. But let's assume that that's the case. I think all of these interfaces need to change. Somehow you need to communicate this information to the memory controller if it's known by the memory chip. But it turns out there are difficulties in actually knowing which the retention time of different rows. The memory manufacturers are not able to do this accurately. Because what happens is as you solder the chip on a DIMM, you get exposed to very high temperatures, and that changes the retention time profile. And there are also some other effects. I'll refer to you to some paper. There are random effects where a memory cell's retention time changes randomly. And to be able to do this more accurately, you would like to do more online profiling, figure out this profile online. And an important research question is how to do that accurately today. So these are good research problems. Your question is very valid. Okay, so what's the mechanism? I've already given you the mechanism actually. Radar consists of 3 steps: retention-aware, intelligent, DRAM, refresh. You profile, the first step is profiling, profile the retention time of all DRAM rows. It can be done at DRAM design time, but may not be accurate in that case, or dynamically. And this is actually an ongoing research topic. The second is you store the binning, store rows into bins by retention time. And we're going to use Bloom filters for efficient and scalable storage. You remember Bloom filters, right? From the first lecture? How many of you do? Sort of. Okay, I'll go over them again because this is another fundamental thing that is very good to know. Okay, I guess this is not working anymore. So if you think of DRAM, it looks like this. And there are only very few cells that need to be refreshed every 64 milliseconds and every 128 milliseconds. So taking advantage of this, you can have very small storage in the controller for that large of a memory. And the last thing is refreshing. Memory controller refreshes rows in different bins at different rates. It probes the Bloom filter, so it determines the refresh rate of a row. So how do you do profiling? I'm not going to go into that, but the general mechanism is you write data into the row, prevent it from being refreshed, and measure the time before data corruption. And you do this for each row. And you can imagine that this may take a very, very long time, right? So if you could do this offline, that's great. But it turns out the retention time of a row is not only dependent on where the row is, what the row is, but it's also dependent on what's stored in that row and what's also stored in surrounding rows. So that complicates the process. It's dependent on the data pattern, because the data pattern determines the interference that happens in the bit lines and the word lines, right? Whenever you access that. It determines the crosstalk. So that's one difficulty. The other difficulty is what I mentioned. Randomly, the retention time actually changes. There are effects due to physics that causes this. It's actually a pretty interesting problem. But we know, so this is, assume that this happens, how do you actually bin? How do you efficiently and scalably store rows into retention time bins? And we talked about hardware Bloom filters, right? This actually is data structure that can store approximate set memberships. That's the idea. And this is one example. You have a bit vector, and if you want to insert an address into this bit vector such that later you can query it, you have these hash functions that are hard-coded in hardware. And if you want to insert that address, you supply that address to the hash functions, and the hash functions map that address to a number of bits, in this case 3 bits because you have 3 hash functions, and you set those bits at the locations that are specified by the hash functions. These bits being set means any address that go through all of these hash functions and map to these same bits are deemed to be present in this set. And assuming that multiple different addresses can map to the same bits, you have false positives. Right? That's why it's approximate. So it's a probabilistic data structure that compactly represents set membership. Whenever you would like to quickly query set membership and you can tolerate false positives, basically you can tolerate the fact that this thing can tell you it is present, even though it may not be present, then this is a good thing. It basically quickly tells you presence or absence of element in a set. It cannot guarantee that an address you supply is absent, but it'll give you present if it's really present. Okay? That's why it's probabilistic. If you want to do a non-approximate set membership, what do? Basically, let's take this example. You have a number of rows in the system. You can associate 1 bit per row, right? All of the rows in the DRAM system, you can associate 1 bit per row. And if this row is in 1 bin, you can set its bit, right? But this is a huge bit vector, right? You don't want 1 bit per row. Instead, we're going to use an approximate data structure, use a much smaller number of bits, basically shrink this bit vector into something smaller. Now you cannot have 1 bit per row, because this was 1 bit per row. And 1 bit per row determines set membership really easily. It's not approximate, it's exact. Right? You set the bit for the row that you want to be present. Now you shrunk this bit vector, and we're going to indicate each element's presence or absence with a subset of these bits. So we're going to map an address, row address, to a subset of these bits. That's the idea. Some elements map to the bits, other elements also map to. That's the unfortunate thing. That's what is a false positive. As long as you can tolerate that, that's great. And there are 3 operations in the Bloom filter: insert, test, and remove all elements. You cannot remove an element exactly because of this, right? Some elements map to the bits, other elements also map to. So let's take a look at this operation example. Let's say we have 1 bin. We've determined the retention time profile of this row 1, and we know that it's 64. It needs to be refreshed every 64 milliseconds. How do we insert that? Basically, we have these 3 hash functions that the row address goes through, and it sets these bits. Why do you have 3 functions? Well, you could have only 1 function, right? You could just use the bits, some bits from the row address, not even have a hash function. But the idea of hash functions is to distribute the bits, the addresses to the bits in a more or less randomized fashion, such that you have fewer conflicts. It's very similar to the cache randomization that we discussed. Whenever you do better hashing, you reduce the probability of conflicts and the probability of false positives in the Bloom filter. And as you add more hash functions, hopefully you'll have more bits over here. Well, again, you may not want to have many, many hash functions over here. Okay, so how do you test row 1's presence? The memory controller supplies row 1's address, which goes through these hash functions and maps to these bits. And if all of the bits are 1, then you say row 1 is present in this filter. And then you refresh it every 64 milliseconds. How do you check row 2's presence? Well, you supply row 2's address in the memory controller. It goes to these hash functions and maps to these other bits. And it maps to one bit that's 1, but the other bits it maps to is 0. As a result, the Bloom filter returns that this row 2 is not present in this bin. And row 2 should not be refreshed every 64 milliseconds. Make sense? Now let's say we insert row 4. It maps to these bits, to these hash functions, and those bits are set. Now let's say we check the presence of row 5. Well, in this case, row 5 actually goes through the hash functions and happens to map these bits that are all 1s. Right? Although these bits were inserted by, I guess, row 1 and row 4. Right? Row 5 we've never inserted, but we found that the Bloom filter tells us that it's actually present. It's actually in this filter. Right? This is a false positive. And in this case, it's okay to have a false positive because you just refresh row 5 more frequently than it's needed. You refresh it every 64 milliseconds instead of every 256 milliseconds. So the benefits of Bloom filters has been false positive row may be declared present in the Bloom filter even if it was never inserted. This is not a problem in this problem because you can now you're going to now refresh some rows more frequently than needed. If your problem is like this, then that's okay. The upside of a Bloom filter is it has no false negatives. Rows are never refreshed less frequently than needed. And this is what you really care about. This. Assuming your profile is correct, this will keep the DRAM correct. It's scalable. A Bloom filter never overflows. So that's, you may have very few rows, and you may decide to store them in a table, right? Instead of a Bloom filter like this. You may actually have a content associated memory and store the address of all rows. And memory controller can actually check the addresses, compare the address that's going to refresh to that, to all of that table. Now this is, first of all, it's content editable memory, so it's expensive. But it's also, it's not scalable. If you want to add more rows, let's say you want to add more DRAM into the system, how do you increase the size of this? Well, you need to provision for the worst case. Whereas Bloom filter, you can keep adding new addresses. You just set more bits. You may increase your false positive rate, but you'll still be correct. And it's efficient. There's no need to store information on a per row basis, as this would be. Yes?
So you never remove anything?
In this particular problem, you never remove anything, right? Because once you insert, the hope is that you've determined that this row retains data.
Oh, like for
At
your
this-
DRAM chip.
Exactly, yes.
Okay, it's going to be more of a permanent thing.
Exactly, permanent thing, yes. But you do scale the refresh rate based on temperature, because what I mentioned earlier, temperature and refresh rate, retention time have an exponential dependence. Retention time reduces exponentially with temperature. But you can just scale the refresh rate. Okay? And removing individual elements is very difficult in a Bloom filter because different elements map to the same bits, right? If you have a problem where you need to remove individual elements, this may not be a good way of representing set membership. Okay, so this is useful when you can tolerate false positive in set membership tests. And I'll leave you with, I'll let you read these papers if you want clear descriptions of how Bloom filters are actually used in hardware. This is what we've discussed, retention of DRAM refresh, but you can use it in caching also, but we don't have time to talk about that. So let me actually wrap up later. Basically, how do you do the refreshing? Now the refresh controller is in the memory controller. The memory controller chooses a refresh candidate row periodically. It determines which bin the row is in, and it determines if refreshing is needed. And if refreshing is needed, it refreshes the row. And this is a little bit more detailed description. You can take a look at that here. So this answers your question a little bit. Today, in the baseline design, in today's memory system, refresh control is in DRAM. Basically, the memory controller sends auto refresh command and doesn't even know which row is being refreshed. So how do you actually implement RAIDER? You can implement it either in the controller or DRAM. You could have it in the controller over here. I guess that's the overhead. You don't need to worry about the overhead, but that somehow the controller needs to determine which rows have what kind of retention time. Right? Somebody needs to form that. And that's an interesting research problem. You could also have RAIDER over here and keep a similar interface here. Right? The memory controller still sends refresh commands, and the DRAM decides to drop the refresh, for example, based on the internal information it has. Now you could do better than that probably, because you may not even need to send the refresh command if you know that it's not going to be and nothing is going to be refreshed. Right? And that's the overhead. Of course, logic here is much more costly, right? Because the DRAM process is optimized for the capacitor, the cell itself. If you add more logic over here, it becomes much more expensive, and the logic becomes slower. That's why it's hard to embed logic into DRAM. Okay, some takeaways. Basically, these are results with a 32 gigabyte DRAM system, 8 core, and a bunch of workloads. The hardware cost with true Bloom filters is that. You can reduce refreshes by approximately 75%. This leads to an energy reduction of 16%, an idle DRAM power reduction of 20%, because whenever the DRAM is idle, in self-refresh mode, you can use this, right? Performance improvement is approximately 9% with these workloads, and the benefits actually increase as DRAM scales in density, because refresh becomes a much bigger problem at 64 gigabit DRAM chip density compared to 4 gigabit DRAM chip density. Both energy and performance benefits increase. Okay, I'll leave you with some questions, basically. What else can you do to reduce the impact of refresh? It's a good idea to think about these. What else can you do if you know the retention times of rows? Can you do something else? One thing that we've discussed is maybe expose to the operating system such that the operating system doesn't allocate pages to these rows, right? Maybe you can do something else, right? If you know the lifetime of data structures, maybe you put data structures that are going to live shorter than the retention time of rows. That way you don't need to even refresh anything if you have that information. And this is a difficult question. How can you accurately measure the retention time of different DRAM rows? And I'd recommend you to take a look at this paper if you're interested in that question. This basically studies a number of DRAM devices experimentally with the FPGA infrastructure that you may see over here. It's an embellished version of that FPGA infrastructure that my students had developed earlier. And basically reports results as to what are the retention time, what is the dependence of the retention time on the data patterns that are stored in memory, what is the dependence of retention time in terms of temperature in modern DRAM chips, and what is the effect of this variable retention time phenomenon where a retention time of different cells jump over time. So this paper contains a lot of that information. Well, I guess I've come to the end of the lecture, but you have more slides to take a look at if you're interested. Any questions? No? I'll let you go so that you can work on the labs. All right. I'll see you later. We'll send you an email as to what will happen to Friday's lecture.